So, Joe, let's begin the meeting.
Yep.
Yeah. Hello everyone. Welcome to the Savnet meeting. So, Joe can only take part in the meeting remotely. So I will make the chair's slide. Uh, First, note well, here is just some remind for the various topic, such as the patent and the code of conduct. Uh, Related to the patent, so we must remind all of the participants that by participating in the ITF, you agree to the ITF, agree to follow the ITF procedure and policies. And if you aware any active contribution that is covered by your patent, you should declare it, disclose it. As a participant, you should know all your activity and acknowledgement will be recorded. During the discussion, you should follow the code of conduct of the ITO process. So here is a summary of our working group's status. Currently, we have five working documents, almost five working documents. There is the draft inter-domain architecture is almost, we will close the adoption call after meetings. For the intra-domain problem segment, we have finished the WJ process. Uh, and, uh, and and there is another document is the Basavi document is moved from the seed operates working group because the question because the solution provided by Basavi is more relevant to our working group. Uh, After this working document, we have about 22 uh, personal document covering the intra-domain solution and inter-domain solution and some general component. We will discuss them today in today's meeting. Here is the goal of our meeting. Uh, First, we will make the intra-domain Savnet architecture introduction and the solution regarding the intra-domain. There are several proposals for the intra-domain solution. Currently, in today's meeting, we will present only two proposals, and I want to all of us to consider how to converge the two proper two different proposals because as one working group, we want to provide only one solution for the IGP for the intra-domain scenarios. I think it is enough. And for inter-domain, there are bar survey and bicon survey. Uh, we want to know how can they solve all the problem, all the inter-domain problems. And we also want to know is there any some new problem that can maybe the lightweight inter-domain because the kind of bar survey and bicon survey all depend on the uh, depend on the RPKI infrastructures. And the last is some new proposal and the OM and management proposals. Uh, so here is the draft agenda. We will divide our introduction into three parts. The first is for the intra-domain and general component. The second is for the inter-domain architecture and the solutions. And the third is the new proposal and some OM management. Okay. Joe, do you have other comment for chair slide?
The only thing I will note is to remind people, I see a lot of people are using it to use the tool. So to put yourselves on the queue when you have questions, and please do ask questions of the presenters.
Okay. So because there are many participants in today's meeting, and we want to remind every painter to uh, confine your schedule time. Okay, let's begin. So first is the intra-domain architecture solution from the Lan Chenqing.
Okay, hello everyone. I'm Lan Cheng from Zhongguancun Lab. I'm going to introduce the update on the intra-domain Savnet architecture. Intra-domain Savnet architecture aims to achieve accurate SAV in an intra-domain network. It introduces the use of SAV-specific information and guides the development of future intra-domain solutions. In April this year, this document was adopted by Savnet, and this time I will introduce the updated version 01. Since September, on Savnet main list, there has been several comments on intra-domain SAV architecture and intra-domain SAV solutions. There has been a discussion about where to deploy intra-domain SAV. To deploy SAV at the edge or deploy SAV on inner routers. There is a discussion, and some people suggest the architecture should be general. And Tony also suggested that the architecture should mention some necessary factors such as CSPF, FRR, and other things that should be considered by SAV on inner routers. And according to the discussion with AC, I think the architecture should guide the solution towards being effective and efficient. So we add a new section in the updated version to discuss where to deploy intra-domain subnet. To reduce deployment overhead and redundant validation, it's not necessary to deploy intra-domain SAV on all intra-domain routers. So future solutions should specify which routers should deploy this solution, and it must provide incremental benefits when those routers incrementally deploy intra-domain SAV. To this end, this section provides some key recommendations and considerations that should be considered by future SAV solutions in an intra-domain network. To achieve the two goals of intra-domain SAV, host-facing routers, customer-facing routers, and exporter routers are vantage points to implement intra-domain SAV. It's because these routers are closer to the source and would be more effective in blocking source-spoofed data packets. And they can clearly determine the directionality of specific source prefixes based on network topology. Specifically, for host-facing routers, they can generate subrules on interfaces facing the host network and block data packets with source addresses not belonging to that host network. And it's the same for customer-facing routers. They can generate subrules on interfaces facing customer network and block data packets with source addresses not belonging to that customer network. And for exporter routers, they can generate subrules on interfaces facing external ASs and block data packets with source addresses belonging to the local AS. In addition to those vantage points, if a solution decides to implement SAV on other inner routers or inner interfaces, that would be more complicated because many other factors will affect the forwarding path from the source to these routers and will affect the computation of subrules. So if a solution decides to implement SAV on those inner routers, it must take factors that will affect forwarding into consideration to ensure the accuracy, and must avoid improper block and has less improper permits than existing UIPF-like mechanisms. And now we have about 2 minutes for open discussion. In addition to these questions, I'd like to hear more feedback on whether it is needed to deploy SAV on inner routers and on the edge. Thanks.
So, is there any questions?
Peter, you're on the queue. Go ahead.
Mike. Peter Pshenak, Cisco. So I just want to express that I agree because I look at the subnet documents prior to this change, and I fully support the idea of moving the subnet function to the edge of the network. It makes a lot of sense. It makes things much easier to deploy and implement.
Thank you.
Okay, speaking as a participant, not as a working group chair, that's why I put myself on the queue. Um, Conceptually, I understand why edge deployments are much simpler, and I like that. I am concerned about how that works in incremental deployments. And so I think the architecture document needs to be very clear about what happens during incremental deployments if there is no provision for internal deployment and only parts of the edge are covered. What do we get? And I'm not saying it's wrong. It may well be the right answer, but I think that the architecture document needs to clearly spell out what the trade-offs are so that everybody else can understand that.
Thanks. In my opinion, I think the incremental deployment means the the I mean sorry. Yes, the self-solution should specify which routers would deploy this solution. So we should first define what is full deployment. And then the supporting incremental deployment means if only partial required routers have deployed this solution, it must be provide incremental benefits. So that's what I think about incremental deployment.
As I said, all I'm asking is that the draft be clear about this. I'm not.
Yeah. Okay, thank you.
So if there are no other questions, we will continue the next presentation. Okay.
Okay, well, I'm going to introduce a new intra-domain self solution called source prefix advertisement for intra-domain Savnet, or SPA-based Savnet. Here are three terminologies. The Savnet router is an intra-domain router that deploys SPA-based Savnet. The single-homed stub network is a stub network, such as a host network, a custom network, a stub OSPF area, or a stub ES that is belonging to or connected to only one ES. The multi-homed stub network is a stub network that is belonging to or connected to multiple ESs. Okay, the deployment scope of SPA-based subnet is at the edge. There are three advantages. The first is these edge routers are closer to the source and thus would be more effective. The second is compared to serve on inner routers, serve on the edge should be more feasible and easier to implement because it would not be affected by FRR and many other complex forwarding policies. The third is it can provide incremental benefits when these edge routers incrementally deploy SPA-based subnets. Moreover, if we already have SAV at the edge, SAV on inner routers will not be needed. So SPA-based subnet choose to deploy SAV at the edge. It will generate prefix allow list or block list on specific router interfaces by using SAV-specific information. The allow list defers to blocking any, but allows source prefixes in the allow list. And the block list defers to allowing any, but blocks source prefixes in the block list. It has three main steps. There are SPA message generation, SPA message communication, and SAV rule generation. In the first step, subnet routers facing a single-homed stub network will generate SPA messages, which contains two main types of information. They are source prefix and stub network identifier. Source prefix contains source addresses that can only be used by data packets received from that stub network. It can be learned from the router's local routes to its stub network, that is, the locally known source prefixes. But As mentioned in the problem statement document, in multi-homing and asymmetric routing scenario, the locally known source prefixes mean only a part of source prefixes of that stub network. So subnet routers facing the same stub network should exchange their locally known source prefixes. And the SNI value is another key self-specific information. It's used to identify which stub network owns the source prefix. And prefixes belong to the same stub network must have an identical and unique SNI value. After that, the Savnet router will provide its spam messages to other routers in the intra-domain network. Although this solution is a protocol-independent solution, it's recommended to communicate spam messages using existing routing protocols by carrying the SNI value with IP information when distributing IP information. And there are other two documents have implemented SPA-based subnet by using OSPF, ISIs, and IBGP. After receiving SPA messages, Savnet routers will generate a allow list or block list. For allow list generation, a subnet router facing a single home subnetwork will generate an allow list on the corresponding interface by including all source prefixes in SPA messages with the SNI of its subnetwork. And for block list generation, subnet routers facing an external AS or facing a multi-home subnetwork can generate a block list by including all source prefixes in SPA messages. And here shows the most recommended use case for SPA-based subnet is deployed on host-facing routers, customer-facing routers, and AS border routers of an intra-domain network, and generate allow list on interfaces facing host network, customer network, or stub network, or stub AS, and generates block list on interfaces facing a non-stub AS. Here is an example, and this is an asymmetric routing scenario that has already been described in the problem statement document. Route A, Route B, and the stub network 1, there is an asymmetrical routing. Specifically, Route A only learns source prefix P1 from its local route to stub network 1, and Route B only learns source prefix P2 from its local route to stub network 1. So Route A will generate a spam message containing source prefix P1 and the SNI value of the stub network 1. Route B will generate its spam message containing source prefix P2 and the same SNI value. After that, Route A and B will generate an allow list on their interfaces facing stub network 1 containing prefixes P1 and P2 because both prefixes has the same SNI value of the stub network 1. And Route D can generate a block list on interface 4 containing prefixes P1, P2, and P3. Now we can compare SPA-based subnet with UIPF. As mentioned in the PS document, if we use strict UIPF on routers A and B in this scenario, it will have improper blocks. And if we use loose UIPF on routers A, B, and D, it will have too many improper permits. But if they use SPA-based subnet, it will accurately block spoofing data packets to meet the two design goals of intra-domain self with no improper block. And we also introduce an alternative use case and two corner use cases. Specifically, SPA-based subnet can also be used on area border routers in inter-area cases, and it can work in DSR scenario and multi-homed stub network. Okay, comments and suggestions are welcome.
So because there is no other questions, we will move the next. Thanks, Lan Qing.
Thank you.
Good morning, everyone. I'm Sheng Nanyue from China Mobile, and my topic is source address validation in intra-domain network. The content we provide self-implementation and use case on access intermediate exist interface, and we remove the self-source prefix flag in this version to avoid the protocol extension. And we also have intra-domain self via BGP and the running code. We conduct experiments and test data in the lab. As shown in the picture, there are three types of source of the devices: access devices, intermediate devices, and the border devices. And we also have three types of interface. Interface 1 and 2 is the access interface, and the interface 3 is the intermediate interface, and the interface 4 is the exist interface on the border as border. And there are two types of sub roles: intra-domain intra-domain interface 1, 2, 3 primarily deploy alloy list rules, and the exist interface primarily deploy the block list rules. And we have two scenarios according to the source prefix is advertised by IGP protocol or BGP protocol. For the self-on access interface, it is recommended to use a allow list rule. And in symmetric routing, we can just generate the self rule directly. And in the asymmetric routing scenario, take the picture below. For example, if the subnet only announce the right prefix, if we employ the strict URPF, there will lead to the false filtering. And in our method, we generate the cell rows based on the high priority and the low priority prefix. We let the subnet announce the prefix with low priority without influencing the forwarding, and we can generate the right cell rows on the both interface of the router A and router B. For the cell on intermediate interface, it's recommended to also use the alloy list rule, and we use the LSDB information of the IGP protocol to calculate the connectivity and the devices and the interface. For example, for the calculation of node A in the scenario 1, it's from its interface A1, we can get the node B, and from the B1 we get the node C and the prefix 1. So we can combine the prefix 1 and the interface A1 to generate the right cell rows. And the verification on the intermediate interface is optional. For the cell on exist interface, it's recommended to use block list rule for filtering. On the border router, we can first calculate the prefix and the ingress interface using the method before. for the intermediate interface, and then we can convert it accordingly into the block list of the existing interface. We have presented the BGP for intra-domain cell before. What's new here is we use the specific BGP community to identify whether the source prefix can or cannot be added to cell interest to prevent the false filtering. So I will skip this and the framework for the limited time, and the running code, the hardware device, and the software implementations have been passed the exam of intra-domain Savnet in this draft hosted by China Mobile in this year. We use the H3C and the RayJ devices. Here's the topology. We use the access, intermediate, and aggregation devices. And here is the results for the performance. We find that there is little impact of the access alloy list, intermediate alloy list, and the block list on the exit interface on forwarding latency. And we test the 40,000 route number in the test, and there is little effect of the on the convergency. And here is the CPU usage and the memory. So summary, the verification also can be optional at the intermediate device according to the architecture draft. And although the verification at the intermediate layer may be limited in this method, but in the context of the hierarchical and the complex networking environments faced by the carriers, the method approach does not incorrectly discard the legitimate traffic, so it's cost-effective and easy to deploy. So seeking comments and ask for adoption call. Thank you.
Peter Pshenak, Cisco. So my question is, you propose to do the checking on the intermediate routers inside the domain using the IGP topology. How are you dealing with the FRR cases where something fails and you have to reroute and the traffic comes on the interface which was not calculated? FRR, fast reroute. How do you deal with fast reroute on the intermediate routers?
Yeah, because we calculate the cell rules according to the connectivity. If the community, if the interface can get the prefix through the connectivity, it will generate the cell rule, and the FRR does not influence this, because all the for example two paths both can obtained from the interface to get the prefix.
Peter, maybe I can help you to explain. You know, in their solution, all the interface within the internal router will be allowed. So not only the sorted path interface.
What's the point of checking then? if we allow all the interfaces. Okay, we can take this offline.
Yeah,
I'm just
yes,
asking, how do you deal with the FRR, which is a common problem here?
Lan Cheng from Zhongguancun Lab. Could you please back to page 4? Yes. Oh, page 4. Yes. Thanks. So in this scenario, I see it is actually is a symmetric routing scenario. It's not an asymmetric routing scenario. So I think it doesn't address the problem in the PS document.
Yeah, at the beginning, if we only the subnet only announced the prefix, red prefix is the asymmetric scenario, and in our method, we announced the low priority prefix to make it make it to become a symmetric routing and get the right sub-role. We are aim to generate the right sub-role.
Yeah, but asymmetric routing will exist. So, okay, thank you.
Okay. First, I want to say, in all of my hats, thank you for actually running tests. Really appreciated that you've got running code and running tests to actually observe what happens. That's really helpful to the working group. To build on Peter's question, which he's correct, we need to mostly take to the list. I want to suggest that you may need a somewhat more complicated topology in order to be able to evaluate how and whether doing the filtering on intermediate routers can add value. How does it cope with topology changes? How does it cope with dynamic changes such as FRR? If you have to allow all possible paths, are you actually blocking enough paths to be useful? Those would be very useful tests for you to run over time. But thank you very much for running the tests and actually seeing what happens.
Thank you.
I think maybe Wei Qian could explain some.
Yeah, so thank you, Peter and Joey, for the comments. I think such as for FRR, all the nodes in the network which run in IGP, it's dynamic updated the routing information. So we have some basic functions. You can running that update the routing information and sub information dynamically. So of course we may need to add some text in the draft, and we run some test that works very well. Thank you.
Hello, Chong Feng Xie of China Telecom. Actually, I have a general question about the relationship of intra-domain subnet with SRv6. With SRv6, we can design it the path based by the source node or controller, right? So the data path can be dynamically generated, right? So in this case, how to configure the access like anomalous rows and how to verify the source address of the packet correctly? That's my question.
Okay, so this is Wei Chang, and I'm also the one cause of this draft. I think Chong Feng raised a very interesting topic, how we verify or how we use subnet methodology to verify the SRv6 path, right? So, SRv6 path, in fact, the address is updated hop by hop. So that is a problem. I think all the methods now we are discussing may not support the SRv6 solution because it's a sourcing router. But I think we should do something on that. But the solution is outside of this scope of the draft. Thank you.
Yeah.
Just want to build on that since I spent a lot of time working with SRv6. Remember that when you talk about checking the source address of an SRv6 packet, you're checking the tunnel address, which is an intra-domain address. And so even the question of what is the appropriate filtering for checking SRv6 is a different kind of question. And we need to be very careful about asking the question because you're not going to be filtering the subscriber source address or the external source address that is in the inner tunnel. That is not a check you can expect routers to perform. So that is, SRv6 is not out of scope, but we need to be very clear about the scope and applicability of our work on that regard.
Yeah, thanks, Joe. There will be one new proposal to try to solution the SRv6 process in the last section. So because of time limit, we can only move to the next slide, and we can discuss a list for the unsolved questions. Okay.
Okay, thank you.
Okay. Hello, everyone. This is Minqing Michael. Recently, I joined Zhongguancun Laboratory, just a couple months ago. This is version 7 of SAP table, so I will go through it very quickly. First of all, I'd like to give a very quick recall of what this is about. So all we know that currently the SAP tool are basically derived from other mechanisms like a FIB, like ACL. So they are not designed dedicatedly for source address validation. So therefore, there are a lot of limitations like scenario coverage, like efficiency, accuracy, etc. So if you want to move the SAP capability move forward, so we definitely need new dedicated design tools for SAP source address validation. So this is what about. We'd like introduce new, various SAP mode to cover different scenarios, like mode 1 for interface closed connected interface, and mode 2 for mode 3 for open connected interface, but for different kind of scenarios. And also we want to introduce, the flexible traffic handling policies. This will open new opportunity for our operators to, by directionally interaction with the security center. Hopefully, they will be encouraging more operators to deploy SAP, functions actively. And the updates about this version, one update is more about the SAP rule expression. In the previous version, that actually we share the one FIB-like SAP rule expression that for all these 3 modes. But then later we feel like that we might be implying that the implementation. So in this version, we jump back to the original way to describe what kind of SAP rule it is. Basically, there are 3 SAP rules for different modes. That is interface-based source prefix allow list, and the source prefix block list, and then prefix-based interface allow list. Another update is about it need to be revised about the validation procedure. Basically, we suggest that we do interface-based validation first, and then do the prefix-based, which is global level validation follow up, and then in which the mode 1 actually is most preferred, should be mutual exclusive with other modes. So this is basically is like a logic sequence between these modes. It's not actually real implementation in your router. Okay. And I, oops. Okay. Also, we got some comments, some related to the self-rule segment design, and some related to how to reduce overhead. Indeed, because we want to move the SAP capability move forward, so definitely we have pay some cost. But how to reduce the overhead? As I mentioned, earlier, that we want to avoid jumping into implementation. So we don't discuss this in the draft, how to reduce the overhead, and also the details about the segment design. I think in this YARN model or BGP-based distribution protocol might be better place to discuss this kind of thing. The other feedback is about why we don't have prefix-based interface allow list, block list, only allow list here. So basically, actually, in the first beginning, we have both modes, prefix-based interface allow list and block list. And later, we got some feedback that these two modes might be, two sides of one coin. That is, if we, block a group of interface, means allow the other or other interface. So this, in most cases, the allow list interface allow list is much shorter than the block list. So we prefer to remain the mode 3, delete mode 4. So this is why in the very beginning we have 4 modes. Right now we have 3 modes because we removed the prefix-based interface block list. But basically, we are open. We want to get more feedback if we have unique value for mode 4, and your guys' feedback is appreciated. Okay, that's all for me. So basically, as I said, that because we want move SAP capability move forward, so the new tools dedicated designed for SAP is kind of must, I think. So that's all. Any comments? And also, we may want to call for adoption. Thank you.
Yeah, thank you. You first. Okay.
Hi, advance you to sorry, the meet echo app doesn't work, or the agenda just fell down, so I couldn't register for the queue. Can you go 1 or 2 slides back to the comments you had so far? This one, yes.
Yes.
I just want to give an extra remark, especially to the memory space of the SAF table. It's not only memory.
Yes, exactly.
It's we are filtering with large SAF tables for like 5,000 aggregated prefixes in most routers. What we find is that's a limit for the table in the FIP. But what we find out as well is the provisioning of the SAF tables makes the interfaces unavailable because of the computation you have to do when you have a very large SAF table. You have to change one entry.
Yes.
It takes some computation, so that's a limitation as well that we need the vendors to look at.
Yeah, yes, that's a good question. Actually, I had a very many discussion with some vendors. Yeah, this is a very tough for new generation SAP capabilities in terms of the forwarding plan design. There was also balance between the memory saving or lookup, how to, get better performance like that. That's always, and how to coexist with other, tables like that. Yeah.
Yeah. Regarding the mode number for where the mode 4 need to be included on, I think you can rerun question on the main list, and we can select the opinion from the participant. Okay. Thank you.
Okay, let's get started. I'm Shuavang from Zhongguanxun Lab, and today I'm gonna talk about remote measurement of outbound source address validation deployment. I have given some presentation at previous IETF meetings, and in this IETF meeting, we submit a draft about remote measurement. So outbound IP spoofing poses a significant threat to internet security, and malicious users often use IP spoofing to carry out attacks like reflective DDoS or DNS cache poisoning. Marrying the deployment of outbound source address validation is critical for characterizing the vulnerability to outbound IP spoofing across the global internet. And the remote measurement of OSAL deployment offers a practical method for marrying numerous ASAC efficiently. Oh, I cannot control
sorry.
slides. Okay, good. So why is local measurement is not enough? To measure if a network can send the spoofed packets, one can try to send the spoofed packets to controlled servers and observe whether they are received. So for a local measurement, if a volunteer in a network can deploy software that actively sends spoofed packets to a controlled server, the network's outbound IP spoofing capability can be easily measured. And this is how KDAS spoofer tool operates. However, this volunteer-based approach does not scale well because it's difficult to obtain cooperation from a large number of networks. So it is essential to develop a method for remotely marrying outbound IP spoofing without relying on active participation from volunteers in the tested networks. So for a remote measurement, if uncontrolled host in the tested network can be elicited to send spoof packets to host outside the tested network, it will be possible to measure the deployment of OSAL without cooperation with the tested network. To remotely measure OSAL deployment, we use destination network address translation to elicit remote hosts to sending spoofed packets. When a packet matches DNAT rules, the DNAT device will change the packet's destination to a preset address while leaving the source address unchanged. This will result in a spoof packet because the source address does not belong to the network. As shown in this figure, first the scanner sends a packet with source address IP1 to the network device with DNAT configured, which is IP2. Then the DNAT device modifies the destination to IP3 but keeps the source address as IP1. This will create a spoofed packet. Finally, by observing the behavior of these elicited spoof packets, we can measure OSAL deployment in AS2. We characterize deployment status in 3 aspects, including presence or absence of OSAL and the filtering depth. Filtering depth represents the position where a spoof packet is discarded when going out the network. And for filtering granularity is the range of IP address that can be spoofed at. For example, if the filtering granularity is /8, addresses within the same /8 prefix as the original IP address will not be discarded. If the elicited spoof packets reach the receiver IP3, then we know OSAL is not deployed in AS2. But if the elicited spoof packets do not reach the receiver IP3, this may be because the OSAL is deployed in AS2 so that the spoof packets are discarded. Also, it may be caused because no spoof packet is generated. So to conform the generation of a spoof packet, we leverage the SMP time exited message, which codes the first 28 bytes of the original packet that triggers time exited message. We can learn the source IP address and the destination IP address of the original packet from the quotation. And if the destination IP address has been changed while the source IP address remains IP1, we can confirm that a spoof packet has been generated. If the receiver does not give a response when the spoof packet reaches it, we can still infer the deployment of OSAL by analyzing the path of the spoof packet. If OSAL is absent, the spoofed packet will travel beyond AS2. Otherwise, it will be blocked and never leave AS2. This is the overall workflow. To measure filtering depth, we first obtain the path of a spoof packet and then take the last responsive hop as the position where filtering happens. Since the DNet device does not reset the TTL field in packets they receive, we increment the initial TTL values in original packets, similar to how traceroute works. By collecting the source IP address from the SMP time exited messages, we can trace the path of the spoof packet. Note that some hops may not respond when TTL expires. This will lead to a conservative estimate of the filtering depth. To measure filtering granularity, spoof packets with various source IP addresses needs to be sent. To this end, the scanner needs to send multiple original packets using only IP1, but also other addresses adjacent to IP2 as the source address. However, to detect whether these spoof packets reach the receiver, we use specific protocols like DNS or increases in IP ID, SMP fragmentation, or SMP rate limiting feature. We use this method. We have measured more than 3,000 ASs and 86% of AS tested by us were not covered by KIDA's proofer in the last year, and 80% of the tested AS shows the consistent absence of OSAL, indicating a still severe OSAL deployment situation. 66% of OSAL deploys at the first hop, and only 3.9% of OSAL is deployed beyond the 3 hops from the DNet devices. Next, I tried to seek feedback and comments. The measurement results are published at our website and updated monthly. Feedback and comments are welcome. Okay, that's all. Thank you.
Yeah. Okay, thank you.
Hello, good morning, everyone. I'm Li Binliu from Zhongguancun Lab. Today, I will present the updates of the inter-domain Savnet architecture. Okay, inter-domain Savnet architecture aims to provide a comprehensive framework for developing new inter-domain sound mechanisms. It is going to address the problems of existing inter-domain sound mechanisms and meet the requirements proposed in the inter-domain Savnet problem statement draft. This is a summary of the historical versions. In total, we have updated 13 versions. After Ietf 1.2.0 meeting, we have updated 3 versions. Today, I will present the version 12. I will go through all the comments and our corresponding responses and the revisions. The first type of comments is about the comparisons of different style-related information. CRM commented that the table in Figure 4 is misleading. In the performance assessment of each data type, the draft appears to assume that there is a solution based on each type of data only. That is incorrect. And there is no need to compare the performance of solution in this document, and because it is meant to provide architectural guidance to the solutions and should not presuppose solutions. So he suggested that this draft should just mention there are various types of data sources for SAO. Xueyan also has the same concern. To deal with this, we have removed Figure 4 in the draft and only introduced the 4 available SAO information sources, including ROA and ASPA objects, local routing information, IR data, and SAO specific information in Section 5. And the second type of comments is about the self-specific information and the communication mechanisms. SRAM commented that we should soft down the statement using the words like it may be expected that. And he also commented that the self-specific information communication mechanism depends on the BGP S-pass information to learn about the interconnections between AS. The S-pass may hide some interfaces that exist between AS in topological scenarios involving fork and merge. Ajun also commented that in the architecture document, we should only provide some requirements for the solutions to cover more scenarios in a general manner. So to cope with this, we have softened down the statement about in section 5. Also, we have added a statement. If the legitimate incoming directions of the self-specific information are learned from the BGP path in the scenarios involved, learned from the BGP path information, it needs to note that the BGP path may hide some interfaces that exist between us in the scenarios involving topological fork and merge. We also have simplified figure 8 and provided a description of the design requirements for the self-specific information communication mechanism in section 7.1. Also, there are comments about the guidance for conducting new potential solutions. CRM recommends that a new paragraph for considering a solution using RPKI and BGP data as a potential BCP for inter-domain solve into the draft. Correspondingly, we have incorporated the suggested draft into section 4. And there are comments on the on integrating controller-based solutions into the draft. Based on the comments in section 4, we have discussed how AS can utilize network controller to communicate self-specific information or distribute self-specific information across AS managed by the same controller when AS supports the network controllers. And regarding to the comments on management information communication mechanism, in section 7.3, we have revised the descriptions of the management information communication and illustrated them accordingly. In sum, we have summarized the comments discussed in the mailing list from Ietf 1 to 0 to now by grouping them into different categories and sorted out the discussion process of different revision suggestions and questions in detail. As well as our corresponding revisions. All the comments and the responses and the revisions can be found at the GitHub page. Also, we have provided our responses to all the questions and introduced our revision summary in the Savnet mailing list as well. Okay, many thanks to all the people from our community for their valuable comments and feedback to help improve this document.
Yeah, sure.
Any comments?
Sure.
Sriram from NIST. So thank you for considering all the comments we discussed on the mailing list and incorporating changes. So of course, I mean, these are the two main issues. One is about the prioritization of the different types of data sources. So that's removed now. There's no priority.
Okay.
So that's good. And so there are two concerns mainly about the SAF-specific data and the SAF-specific communication protocol. Like I pointed out, one of them is about the hidden hidden interfaces, and the other one is the security, like which we discussed most recently. If an AS is communicating to another AS about the SAF-specific data, the other AS doesn't know whether the sending AS is in the customer cone or in the customer cone of a lateral peer or in the provider cone. So the first AS can try to fool the second AS. So the security or the trustworthiness aspect there needs some more consideration. So because of these reasons, it is good not to prioritize these data types and also not say that the trustworthiness, for example, for SAF-specific information is still to be determined. So a few things like that will soften the document rather than tilt in one direction or in favor of one type of data. So we just need to stay focused on that and get the document right.
Okay. It's some about the details of the solutions. So we will consider it in the solution, right? So for the architect drafter, we will update accordingly. Yeah, thank you.
Okay, thanks, Libin. Sarah?
Let's press these.
Yeah, you can control it.
Good morning. I'm Sri Ram from NIST. This is joint work with Igor Lubashev from Akamai and Doug Montgomery, also from NIST. So we have presented this work before in both CyberOps and also in Savnet once. I just want to go through some description about the protocol itself briefly, but then some new issues that we have discussed recently. I will try to focus more on that. So this proposal, BAR-SAV, which makes use of BGP, AS path information, ASPAs, and ROAs for generating the SAV table. So it makes a complementary use of these three types of data. It significantly improves the ability to detect hidden prefixes. I'll talk about that. And also it provides a solution for the CDN and direct server return DSR problem. It doesn't require a change in the protocol on the wire. It requires no new protocol on the wire, and it offers immediate benefits to early adopters. We focus primarily on the customer interface, a SAV table, generating a SAV table for the customer interface or a peer interface. In each case, we look at the customer or the peer, and we look at their customer cone and try to determine what are all the prefixes that exist, what are all the ASs and prefixes that exist in those customer cones. So it's a common solution that applies to both the customer interface and also for a lateral peer interface. So prior to BAR-SAV, we had RFC 8704. In a nutshell, what it did was it improved upon the feasible path URPF, and so we have an enhanced feasible path URPF, EFP URPF, which is in 8704 RFC. And in that, we look at the AS path routes received, AS path in the routes received in any direction from the customer interface we are interested in, as well as the lateral peer or provider interfaces. We look at all the AS paths, and once we know that one of the ASs is a customer, and if that customer AS appears in any of the other AS paths, we also take the prefixes that are announced through those AS paths, whether it is from a lateral peer or a provider. So that way we try to make the SAV table more inclusive of customer interfaces. We improved upon that in BAR-SAV. That's just using BGP at this point, not ASPA and ROA. It's just using BGP. We improved upon that a bit by considering not only the origin AS in the path, but also the intermediate ASs. Because if I receive an AS path from a lateral peer or a provider, and I recognize that one of the ASs is in my customer cone already, I know it, then I can also include those prefixes. So that is an improvement. So in this picture, for example, only P1 can be recognized through BGP on the direct interface with the customer AS1 if we are doing SAV at AS4. But there are another prefix, P3, for example, which can also be picked up, even though it's not announcing it on that interface. AS1 is not announcing on that interface. P3 makes its way through another provider to AS4, and since AS4 already knows AS1 is in the customer cone, it can pick up P3 also. So that's an improvement of BARSAV over EFP URPF. So BARSAV now, what it primarily tries to do is it tries to make use of all three different data sources, BGP, ASPA, and ROA. It goes systematically down the customer cone step by step recursively, and it tries to gather all the ASS from the ASPA data and also from the BGP data. So we have a fairly detailed algorithm, which is well described, I believe, in the draft. That if you look at this picture, I won't go through all the details of this picture, but this picture, if you look at it, you would be able to see that any type of prefix that is applicable to that particular customer interface from AS4 to AS3 can be detected by using the BARSAV algorithm. So there are clever ways in which you can use BGP to detect what are the ASS in the customer cone, and then you can use the BGP updates as well as ROAS to pick up the prefixes that are applicable to those ASS or that originate from that AS. So by doing this, there are a variety of things here. Partial deployment is considered here. And in that case, ASPA, for example, steps in to make up for picking up or discovering a prefix that is hidden in BGP. And if there's partial deployment of ROA and ASPA, BGP will step in to try to help discover prefixes that are missing in ASPA or ROA. So in a very complementary manner, it works to complete the picture, to collect all the applicable prefixes for SAV. So we took care of the DSR, CDN situation. I think most people here know well about that. There is a problem of hidden prefix in the case of CDN, the direct return server. So with the help of ROA, that can also be gathered for SAV. Now, the no export and DSR scenarios, we need to make a few recommendations, strong recommendations to the network operators. One of them is to register ASPA in case of origination of routes with no export, and or advertise a covering less prefix also without no export to the same providers. So I generated a discussion on this on the NANOG list, and there was good feedback from the providers to say that, yeah, indeed, when you have a no export situation toward the provider, you should definitely try to include less specific also towards those providers. Then registering ROA in the case of unannounced DSR anycast prefix, we also need to make a strong recommendation about that. So with these two, we would be able to take care of hidden prefixes. So there are some delays, questions arise. What about the RPKI propagation delay? Does it affect BARSAV? It really doesn't affect BARSAV because first you have to take care of RPKI propagation delay in order to be able to do ROV correctly, and also to be able to do ASPA route leak detection correctly. So the first two bullets are like if you have a newly registered prefix already announced, the ROVA status change will only change from, if you're creating a ROVA for a newly announced, you're creating a ROVA, registering a new ROVA for a prefix that's already announced. In that case, the ROVA status only changes from unknown to valid, and that has no impact on accepting the route based on ROV or on BARSAV. So similarly, if ROVA is newly registered for a newly acquired prefix, in that case also one can start announcing the prefix right away before the ROVA has propagated through RPKI. The ROVA status changes from unknown to valid and has no impact on BARSAV. Now the next two bullets are important. One of them says that existing prefix with ROA is split and more specific prefixes under it are announced. Then a new ROA is propagated, and the recommendation is that the operator should use make before break principle, and that helps both ASPA route leak detection, and also BARSAV. The idea is that you withdraw the less specific prefix and the old ROA only after the new ROA has propagated. Similarly, a precaution has to be followed in the case an AS has a new transit provider and ASPA is updated. And running out of time, I've shared this with the authors of the inter-domain architecture document, and I pointed out that in the case of BARSAV, in a scenario like this where there is a fork and merge, there is no issue with BARSAV because BGP can correctly identify the prefix and there are no hidden interfaces. But the hidden interface problem occurs with whatever currently has been described about the SAF-specific solution. So that's something that authors and myself have discussed, and the authors are taking steps to take this into consideration for the SAF-specific data source. So with that, I can stop. Thank you.
Yeah, a quick question. Would you like to back to slide 6? Slide 6. Yeah, here you have said the step for building the save table, but you think you will get all prefix in IOA, but one AS may have many prefix, but not all of them announced in the BGP. So if you get all the prefix in the IOA, will the save table in the router be there are larger unnecessary prefix?
No, there wouldn't be.
Because such prefixes aren't be advertised. So why you get all the prefix?
Yeah, so unadvertised is okay because they have included the prefix in the ROA and they are not announcing it yet, but we include it in the SAV table conservatively. So in order to minimize, and because they could be announcing it anytime because they already have a ROA, so we want to be prepared for that.
Okay,
it won't increase. It will make sure that there is no blocking.
I know. So you just don't want to block any prefixes. So you allow all the prefixes as have.
Yeah, that are legitimate on the basis of either BGP or
I know. I think we can find some even more efficient measure to solve the problem. Okay, thank you.
I see, Ram, this meeting, Mike. Just very minor comments. As from my understanding here, ROR and ASPA here is helpful to finding hidden prefix and hidden ASs in cousin core. But given that you also mentioned, given that the deployment of the ROR and ASPA could be long run, so in short term we might be not available. Is that a good choice that we can get those information by local management also? Okay.
Yeah, you gave that comment on the list. We can discuss that further.
Okay.
Thank you.
Maria, developer of BERT, I'd like to ask whether there would be also a good idea to maybe define a new BGP community for, on the other hand, sending something like we want to accept ingress traffic for these addresses, but we won't ever send data from these addresses back, because we are using the direct return.
Using a community, you want to communicate that information.
Yes, yeah. I want to say I want to send a route saying yes, I want to accept data for this, but I don't want you to accept any data from these addresses. Block it in the other way.
I think we need to consider the security. ASPA and ROA already come with security built in. We need to consider the security aspect of that using a community. If someone can abuse it and interfere with the SAV table generation in some way. But I would like to discuss it with you one-on-one in more detail about that. Thank you.
Alexander Azimov, younger. So, as far as I understand, you propose to apply this technique on the customer facing links, right?
Or lateral peer. Yeah.
Yeah. So not applying it at the peering links.
Not applying to what? Provide?
To peerings. So we have customers, we have providers, we have peerings normally in inter-domain routing. And you are suggesting to apply it only to customer links, right?
Customers or lateral peers. The two types of interfaces.
C2P.
Sorry. So AS6 is a customer, and 7 to 6 is a customer interface, or AS6 could be a lateral peer, and that's a lateral peer interface.
So okay, I have two comments. First comment is that I have scenarios when, as a CDN provider, I have a peering link with a neighbor, and I don't have any BGP announcements to this peer. I will not register a SPA record either, because it's a peer, not a provider. And it will be a link that is fully invisible in your technique. The second question is just a general concern.
Yeah.
That can you get back to the last slide?
Oh, the one we had?
Yeah, just the last slide. The last slide.
This, you mean?
Yeah,
okay.
just this one. So today, if root leak happens, it may affect your network connectivity or may not. But in this scenario, if IS2 leaks to IS3 at default route, it will result in a packet loss. If someone of the upper transit providers will implement this technique. So I don't want to be punished because someone else made a mistake by configuring its routing policy. So I see here an opportunity for a lot of false positives.
So on the first question, DSR, I would like to discuss some more with you. I spoke with Igor at Akamai. My understanding is that the DSR AS is generally a customer, not a lateral peer. So we can discuss that offline.
It can be a peer. It can be a paid peer. It can be even free of charge peer. It's all kind of peering relations that can happen between CDNs and its neighbors.
Yeah, we can clarify that with Igor and Jared, because they are Akamai and they do this in their network. So we can clarify that question. And on the question, the second question of whether I think you're asking if route leaks somehow are not detected, then they may generate some errors in the SAV table. That you may be including prefixes which are there due to route leaks. But our assumption here is that with the help of OTC, with the help of ASPA, we are detecting the route leaks. We are detecting the bad prefixes using prefix lists as well as ROV. So we are assuming that you are accepting these BGP updates already to install, to consider them for best path selection. So at that point, we are assuming that those are the only routes we would consider for BARSAV. And so there is that kind of cleaning up the route leaks and the hijacks already happened because of various techniques that are applied to BGP to detect and eliminate them. So that's why we are assuming that there is sanctity about the data at that point.
If we are speaking about a perfect world in the post-route leak era, I would agree. Yeah. But I can't imagine it in any time when we live in the world of incremental deployment. Thank you.
So thank you for coming. We also need to keep in mind that it is okay to have an extra few prefixes in the allow list rather than not have them. What is important is to keep the blocking of legitimate source addresses at 0. So that is why being conservative is favorable.
Yeah, thank you. So, okay. Next.
Hello everyone, Lan Cheng from Zhongguancun Lab. I'm going to introduce the updates on BiConSav. BiConSav is an inter-domain self solution which generates and uses a block list self filter. It's also used on interfaces facing a custom AS or lateral peer AS, and it helps avoid improper block in the case of limited propagation of prefixes in customer code, such as the no export cases, which has been described in the RFC H704 and in the inter-domain problem statement draft. And in August, we have requested an adoption call in Sadrop's working group. And after that, this document is moved to Savnet by agreement of chairs and ADs. It doesn't work. Okay. During the adoption call, we have received significant support from many people. And this document is moved to Savnet because several people have spoken that this document doesn't fit the charter of Sadrop's will. And we also received some technical comments from Siriam and Eagle. For example, they said there is an improper block of invisible prefixes by both Basel and BICOM. And to further avoid improper blocks, we update the design of block list generation in Section 5. And SRAM also said the current BICOM would admit all special purpose prefixes, allocated prefixes, and announced prefixes. To reduce such improper permits, we update Section 7 to provide more implementation and operations recommendations. Let's have a quick review of improper block of using an allow list. In this case, AS1 is a multi-homed custom AS. It attaches no export to all prefixes announced to AS2. This scenario has been described in IFC H704. In this case, if AS4 use EFP UIPF on the interface facing AS2, it will have improper block problems. And more recent self-solutions can use ASPARS and ROAS to fill this gap, if the necessary ASPARS and ROAS are existing. But if that ASPARS and ROAS are missing, it will still have improper blocks. So BiConSav is proposed to achieve the two goals. The first goal is to avoid improper block in no export and DSR cases. The second goal is to maintaining directionality and to identify more source-spoofed data packets than loose UIPF, because currently many ASAs can only use loose UIPF to do so. And the first goal is more important because for many networks, improperly blocking legitimate traffic is unacceptable. The key idea of BiConSav is to generate a block list containing prefixes only belonging to the provided call. It's because these prefixes should not be used as source addresses of data packets received from customer call or from lateral peer AS. And we can use loose UIPF and block list together on these interfaces. Loose UIPF can block data packets using unallocated prefixes and unannounced prefixes, and the block list can block data packets using source addresses only belonging to the provider call. There are three steps. In the first step, BiConSav first identifies as many ASs in the protocol as possible by using BGP updates and ASPAR, and then it identifies prefixes belonging to these ASs. In the third step, it should remove prefixes that may also belong to any customer call. Since an AS may not know if a prefix is belonging to its customer call, to avoid any potential improper blocks, BiConSav removes prefixes that are belonging to both ASs in the protocol and ASs not in the protocol. And we compare BiConSav with the existing self-solutions. There are, in these two scenarios, prefix P1 is single home to AS1 or is multi-home to AS1 and AS66. The BiConSav and loose UIPF should work the best. But there is a challenging scenario. If prefix P1 is single-homed to AS6 in BGP updates and ROAS, but AS1 will still use source addresses of prefix P1, both solutions will have improper blocks. One possible solution is to manual configuration the allow list or the block list. And here is a summary of recommendations. If the network operator can determine that the allow list is complex, it's recommended to use the allow list. If not, it's recommended to use block list together with LUCIRPF, and network operators are allowed to manually modify or configure the block list. Thanks.
Is there any questions? Okay, thank you.
Hello, everyone. It's Xueyan from ZTE. I'm talking about BGP operations for inter-domain SAM. This draft has been presented during the meeting 118, 119. This is the third time for the presentation. The latest version made some key updates. First is about the method change from POI to SDI. And the second one is about to use a BGP policy-based solution and make some corresponding editorial modifications. Okay. For this draft, this slide shows two figures to show an example for the inter-domain subnet scenario. It's about multi-homing scenario, and the filtering location is considered to be set in the closest to the attacks. And to mitigate the source address spoofing, the security requirement is raised in this draft. Its objective is to secure the incoming interface as the right interface, receive the packets. This is a general description for the BGP policy-based solution. It includes SDI and two BGP policy. One is for the export policy and ingress filtering policy, and subnet rule generation and decision process. A key concept for this draft is about SDI. SDI is defined as a tag used for BGP source prefix, secure domain identification. And in this draft, we use a mapping policy between SDI and with the source prefix. And the SDI in one specific secure domain is a unique value. And for the SDI management, it can be managed by a subnet agent, a network controller, or network management system. A secure domain actually can passes the root prefix and or routers within that. This is the detailed for the policy detail, the policy-based solution. Actually, except the secure domain assignment, the BGP export policy is used for the SDI advertisement. SDI will be advertised alongside the prefix advertisement. And in the incoming direction, we also need to set BGP import policy. This policy will set interface SDI mapping policy, and this policy will achieve, the packets received filtering. And the SAM rule involve two aspects: prefix and interface relationship. The decision process actually will need to, based on the validation state, apply some rule in the incoming interface and get the validation date, and then make decision about the traffic transport. And in this draft, we also provide some scalability for the SDI solution. The SDI actually, based on the deployment or implement requirement, it can be set as AS level, BGP community level, router level, and prefix level. It means that for a separate AS, it can be set a specific secure domain, and in this AS, some routers or some specific prefixes can be set as other secure domain. Okay. And for the security considerations in this draft, except to follow the security considerations in the inter-domain Savnet architecture draft, it also need to consider SDI communication security. It may involve the SDI assignment and processing security. So that's it. Comments and feedback. Come.
Libby.
Okay, Libby Liu from Zhongguancun Lab. I have a quick question. How does this proposal address the problems proposed in the inter-domain Savnet problem statement draft in the asymmetric routing scenarios, such as no iSpot and DSR? Because in these scenarios, there some prefix may not be propagated in the BGP announcement or have limited propagations.
Yeah, actually, in this draft, we mainly provide some scenarios such as these two figures. It's about multi-homing scenarios.
Maybe we discuss it offline. I think
Yeah,
it is
okay.
not related to the scenarios proposed in the problem statement draft.
Okay, we can discuss offline.
It seems your proposal just solve the multi-home scenarios.
Yes.
Oh, okay, thank you.
Do you have some suggestion?
I think you should compare with other proposal for the inter-domain solutions and also the architecture solutions. Okay.
Hello, everyone. Hear me?
Sorry.
Yeah, my name is Tong Tian, and yeah.
I will share the slide to you, and you can control it yourself.
Oh, thank you, thank you. And the slide hasn't shown on the screen. Okay.
So I think you can control now.
Let me try. Okay, no problem.
Yeah, let's begin.
Okay. Hello, everyone. My name is Tong Tian, and my topic is source address validation enhanced by network controller. First, wait a minute. First, let us have a quick review of first version in last Ietf meeting. Many newly proposed self-address validation, source address validation mechanisms take a distributed manner to generate sub-rules, such as IGP-based and BGP-based subnet solutions. They acquire source prefix of other subnets within intra-domain or inter-domain networks, utilizing BGP or IGP extension. All devices acquired, important devices are required to support Savnet in order to ensure accurate validation. but they are faced with accuracy and manageability challenges in several scenarios. So we focus on the scenarios and the requirements for centralized subnet, including challenges and limitations of distributed subnet in incremental or partial development scenarios with special IP addresses such as anycast prefix, config and manage routers, flexible and automatically. So we proposed the network controller-based solution for enhancing subnet's capability in intra-domain and inter-domain networks, which supports accurate verification, automated configuration, threat analysis, traceability, and visualization. This is not a replacement, but an enhancement of distributed solutions. Okay. Let's see the changes in version 1. First, it's a centralized subnet capability enhancement solution. We will give overall framework function of each plane, interfaces between subnet controller and devices. Then introduce the intra-domain and inter-domain subnet centralized framework. Okay, we give a high-level view of framework, including subnet management plane, control plane, and the devices data plane. Management plane is responsible for monitoring, configuring, and maintaining subnet devices and non-subnet devices, including deliver the configuration to devices, displaying and managing substrate prefix and sub roles on devices. Then the subnet control plane is responsible for generating sub-rules. And then the subnet device data plane is responsible for maintaining and updating subnet entries from different sources. And the send and the forwarding packets for data forwarding plane. And the sub-rules may be derived from several routing protocol and the control lines well. And the following interfaces are defined. First is report the network topology. Basic BGPs can advise the network information to the controller. Second is report source address prefix and subnet capabilities of network devices can use extended BGPs or YAM model. The third is report sub-rules. The protocol extension of BGP link state to collect sub-rules generated by different protocols can facilitate the multi-source sub-rule monitoring and management through a centralized controller. And the first is deliver sub-rules through YAM, BGP, and BGP FlowSpec and other interfaces. The next slide is we will introduce the intra-domain subnet centralized framework. The controller can implement different control places based on roles of devices. And for ASBR, controllers collect the source address prefix of all subnets in AS and remove special IP addresses and generate the sub-rule or policy in blacklist mode and sends to ASBR. And for access router, controller can generate complete cell entries to avoid false blocking. And for the inter-domain subnet centralized framework, scenario 1, centralized controller in single management domain with multiple AS. The unified controller can deliver sub-rules to the devices of each AS as required. And based on prefix of Intel AS relationship between AS and the third-party authentication information, controller can calculate the sub-rules of the Intel management domain. Scenario 2, different AS have different controller. Each controller can collect complete prefix of its AS and send it to SBR. and SBR can generate sub-specific information and advertise to neighbor AIs. Scenario 3, if SBR do not support Savnet and cannot generate inter-domain Savnet-specific information, it can be advertised through network cooperator for rapid development. So now that we have seen there are several centralized interface extensions and young models. The first is signal Savnet capability and the source prefix used for SAV to controller use IGP and BGPIS. The second report multiple source SAV rules using BGPLS extension. And the third allow operators to manage SAV configuration in heterogeneous environment with routers supplied by multiple vendors. And the fourth and the fifth is to deliver some rules, use BGP or BGP flow spec. And the last, introduce OM by controller for intra-domain Savnet. So can the centralized Savnet framework document be adopted after the 5 turn? And we will end several use cases next time. Okay, that's all. Any questions?
Jeffrey.
Good morning. Thanks for your presentation. I like a lot of things in here. One of the things that is important to point out is that even though I like BGP-LS for a lot of these purposes, the primary thing that BGP-LS distributes is traffic engineering interfaces rather than IGP topology. This isn't to say that BGP-LS couldn't carry IGP topology, but it's not the guaranteed base case. So you may want to note that as part of your proposal.
Okay, thank you.
Hi, Lancheng from Zhongguancun Lab. You introduced the framework at a high level, but I didn't see the design of solution, and I didn't see how this can address the problems in the PS document. That's my concern.
Okay, and I think we can have a communication after the offline, after the meeting, and we can talk more about the questions, and we will add some the solutions to the draft.
Actually, a similar question from here. Yes, because actually I'm thinking that this is kind of a centralized control system that quite challenges in some cases. So, for example, for different scenarios, what kind of information we have to connect and make sure we can calculate that the legitimate interface for different source preference. That in general, the architecture is fine, but when we look into the details, we may think about different scenarios, what kind of source need to be collected and what kind of algorithm is visible like that.
Yeah. So we have no time. We'll make the next practice. Xueting.
Oh, thank you.
Yeah, I see you can control.
Yes. Now it's an overall and general solution. It really lacks some the source information. So we can add the what kind of source needed to be collected and into the draft. Okay, thank you.
Xuting, okay?
Okay. Can you hear me?
Yeah, it's okay.
Yeah. Let's start. Hello everyone. My name is Li Xuting. I'm from China Telecom, and my presentation will run below aspect. And in existing intra-domain saving mechanism, there are two prominent trends. In option A, the shortest path based on GP saving is deployed to allow traffic only along the shortest path. In this setup, it doesn't consider policy-driven routing or dynamically path adjustment. As a result, this reducing may lead to packet loss and unreliable service, as savvy forced to accommodate necessary path change in complex network environments. And in the option B, this approach relaxes savvy enforcement, allowing all interfaces to accept packets without strict path validation. With all interfaces open, the network is more susceptible to both the traffic or malicious injections. So based on the option A, we add SR value policy based survey mechanism to ensure controlled yet flexible survey routes along SR paths and alternate routes as needed. And let's introduce our solution with this use case. In the case of establishing the shortest path based on IGP, service is deployed to allow traffic only along the shortest path, like, for example, router 1, router 2, router 4, router 5. Let's take the router 4 as an example. Interface 1 marked in red allows traffic from router 1 along the shortest path. Router 4 will validate that traffic received from interface 1 follows the shortest path, and if confirmed, will forward it to the next hop. If traffic arrives from interface 2, green path from router 3, router 4 will block and discard the traffic as it's not part of the shortest path. This strict policy infers security but lacks flexibility. For example, if router 2 falls, traffic could reroute through router 1, 3, 4, 5, but router 4 will still drop packets from router 1 due to the strict shortest path rule. And in the fully open scenario, router 4 will would keep all interface open, allowing traffic from any neighboring router. This setup reducing security as any path can pass through, allowing potential supposed malicious traffic. Our proposed SR policy-based survey mechanism offers a balanced, flexible approach. With an SR policy site to reroute traffic along router 1, 3, 4, 5, router 4 dynamically open interface 2 to accept traffic from router 1. This on-demand interface control allows router 4 to adapt and validate traffic from alternative paths specified by the SR policy, while still maintaining strict control over unproved paths. And this mechanism avoids the rigidity of shortest path only setup and the insecurity of fully open setup, achieving a flexible and secure balance. And compared to 7 mechanism limited to each node, our approach also increased security by enabling demand validation within the network core, ensure legitimate traffic is received along dynamically assigned paths, while unauthorized paths remain closed. And the following two pages are the forwarding logic for message propagation and self-rule establishment based on our SRV policy-driven solution. I won't go into detail about the forwarding logic here. Those interested can check out our draft. Our draft introduce a survey based on SRV policy to achieve precisely this controlled interface open. Survey becomes adaptable and can still validate the source addressed to along the expected SR path within the constraint of the shortest path survey. This not only maintains structured security, but also allows for reliable, flexible routing, ensure performance remains optimal even as paths change. And here are some references from our draft. That's all. So thanks for your attention. And
yeah, there are some person will want to ask question.
Lan Cheng from Zhongguosun Lab. Could you please back to page 2?
Yes.
And next, the problem, the limitations of existing intra-domain self solution.
Page 4.
Yes.
Yeah.
Yes. I think sparse-based Savnet has already addressed these problems. And I saw another use case is about the edge-only self. Maybe the next pages.
Is this?
Next. Yeah, yes. You mentioned that the edge-only self cannot protect against malicious traffic from internal nodes. So I don't know why internal nodes would send malicious traffic. If you look at the early version of the intra-domain problem statement document, there was a scenario about malicious internal nodes, but that case was removed because several people have spoken that that is not really happening.
Because in larger complex network, just relying solely on survey from each node may not be to provide comprehensive protection, as internal nodes may attempt to send malicious traffic through non-standard paths that are not detected by its survey mechanism.
Yeah, it's because it's difficult for us to identify which routers is trusted in an intra-domain and which routers is are not trusted. So I suggest we should focus on spoofing traffic from the host. Thank you.
Yes, thank you.
Yeah, Maria.
Maria, developer of BERT, once again. I'd like to ask if that host is able to spoof some traffic. Isn't that host also able to spoof the routing traffic, the control plane traffic, to actually advertise invalid routes and make itself a valid sender in the eyes of the others?
Yeah.
I think you can take your question on the list. Okay. Thanks, 徐婷。
这个问题我有点。
Okay, good morning. I will present the updates of the draft of CSP object. For this document, we have updated 3 versions in total. Today, I will present the version 02. Before introducing the updates of object, I will repeat the background for this object. First, remote peering is needed for Savnet adopting AS for exchanging sub-specific information with a remote one in the partial deployment. This is because maybe the first reason is that IS whose source prefix is spoofed and its neighbors may not be on the path of the spoofing traffic. And the second reason is that IS may want to use the adopting as near the attacker to filter the spoofing traffic. As shown in the right figure, S1 and S4 may want to establish the Savnet connections. For this connection model, it can scale for exchanging some specific information between the AS and more AS deploy Savnet by following their operation recommendations. The first one is that limiting the maximum number of Savnet peering connections for AS. And second one is that leveraging the connected peering Savnet adopting AS as agents to help forwarding their information instead of their direct connection. Okay, so CSP object is proposed for automatic peering. As shown in the right figure, the Savnet agents or S1 and S4 may need to find other Savnet adopting AS and determine the ones to establish connection to exchange the information. So automatic peering can help reduce the operational overhead and accelerate the connection establishment process. So CSP proposed a public IPKI registry to contain the OS, which deploy Savnet and are willing to set up Savnet connections. A newly adopting AS can use this registry as a reference and pick the appropriate AS to set up Savnet peering relationships. So this is a summary of the comments. Most of all of them are from Russ. The first one is that Russ commented that S.1 in the document incomplete, cannot be compiled. So Russ provides an S.1 module that compiles. Russ also suggested us to change the name of the address family in the document. And he also reminded that 2 OIDs are needed in the inner considerations. Okay, based on the comments, we have updated the document. Here is a summary of the main updates. We have revised the name of the content type of our CSP object, and we have revised the ASN.1 module and update the class name of the address family and the name of corresponding elements and the format of AS1.1 module. And we have revised the validation step for the CSP object, and we also revised the inner consideration section. Okay. For the detailed updates of the CSP object content, first we have updated the format of SN.1 module to make it be compiled correctly. And we have revised the class name of 2 IP family addresses. The element here, the element IP family addresses contains a sequence which contains 1 instance of IP family and 1 instance of IP addresses. The field IP family contains an octet string which is either IPv4 or IPv6. And the field IP addresses contains a sequence of IP address instances. Okay, for the we also updated the inner consideration to and we we write the two OID in the need for two OIDs here. Okay, for next step, we are going to implement the CSP based on our OP. And any comments?
Yeah. Thank you, Libin. There are three present cannot be present. Now we can only move the next meeting. Joe, do you have other comment? Okay. So thank you for all of you, and let's meet next meeting.